Metal Additive Manufacturing, Design for Additive Manufacturing. This video has been produced in projects I2P, from idea to printing of metal products and hybrid, efficient applications using multi-method production. Both projects have been funded by the European Union. There are a very large number of different manufacturing methods, and their variations. In the figure below, they are organized into 8 groups. When considering the manufacture of a part, its manufacturing process usually involves the use of several manufacturing methods. That is, for example, a part made by casting is very often machined after casting. A part made of sheet material, on the other hand, is typically first cut, then formed and possibly further joined to other parts, for example by welding. Designers have a very big influence on the methods that a product and its parts are manufactured. The choice of manufacturing methods is, of course, influenced by the cost-effective implementation of the technical requirements. Additive manufacturing differs relatively much from other manufacturing processes, and these differences allow the method to offer unique opportunities and freedoms to design. The general rule of thumb here is that if a part can be manufactured economically using a conventional manufacturing process, it may not be worthwhile to manufacture using AM methods. Parts that are well suited for AM methods have in common is that they are able to take advantage of such AM process advantages as complex internal and or external geometry, custom geometries, low production volumes, etc. On the other hand, as AM methods and materials evolve and new solutions enter the market, the scope will also expand. By the way, did you know that we currently have about 20 different commercial AM processes for metal 3D printing available, and the number is constantly growing? The figure shows 18 different metal AM processes. Currently, powder bed fusion is the dominant method. According to the AM Power Report, 85% of sales last year, so year 2019, were PBF equipment and 8% directed energy deposition equipment. The report estimates that within 5 years, PBF equipment's share of new equipment sales will fall to 63% of total sales, although it is estimated to grow by about 28% annually during this period. In view of the above, the focus in this presentation is on designing for the laser powder bed fusion method, but they are to some extent applicable to other methods as well. It is essential that the designer understands both the advantages of the metal AM method he utilizes, and the limitations of the method. Additional manufacturing may allow, for example, the assembly to be reduced to a single piece. For this reason, it is worth taking a broader view of manufacturing methods already at the stage of considering assemblies. The figure shows a simplified product design process. In that first stage there is a so-called conceptual phase, that is the phase of ideation and preliminary design. This first step is to specify the requirements and characteristics of the product, and to establish guidelines for the structure of the product, and for the design and manufacture of the product. The result of the first phase is a more detailed product description, and a product design and manufacturing concept. In the second step, more detailed design is done in this DFA, design for assembly, and DFM, design for manufacturing, approaches, as well as possible other approaches and criteria, such as manufacturing cost, recyclability, serviceability, etc., are designed according to product requirements implementing product. When considering additional manufacturing in the process described earlier, it will be appreciated that at the stage of considering the assembly, that is dividing the structure into parts, it is worth considering the possibility of combining many parts into one part. When looking at an individual part, there are individual part design guidelines for additive manufacturing. When starting to think about the design of a product or part, it is worth considering what kind of manufacturing methods are utilized, and how their utilization affects the design. Design for manufacturing and assembly, DFMA, is a way to design products so that they are easy to manufacture and assemble. It is therefore a matter of optimizing the design of the product, assembly and part in order to make its manufacture and assembly cheaper and easier. DFMA is usually utilized in the product design phase, which makes it easier and cheaper to reduce manufacturing costs, but the method can, of course, also be utilized in the further development phase of the product. DFMA is based on 11 design principles. 1. Minimize the number of components. Installation costs are reduced. The end product is more reliable because there are fewer connections. Disassembly for maintenance and repair is easier. A lower quotient usually means that automation is easier to implement. The number of parts in the manufacturing stage is decreasing, and there are also fewer problems related to inventory management. Reducing the number of parts purchased also reduces costs. 2. Use a modular design. Each subassembly should consist of 5 to 15 parts. Maintenance and repair are easier. Automatic and manual configuration is then easier. Stock requirements are reduced. The final assembly time is reduced. 3. Use standard commercially available components. Planning time is shortened. There are fewer part numbers. Inventory management is easier. Volume discounts may be possible. 4. Use common parts in different byproducts. As the production volume of a single part increases, automation of production may be more profitable. Volume discounts may be possible. 5. Design for ease of part fabrication. Net shape and near net shape processes may be feasible. The geometry of the parts is simplified, and unnecessary properties are avoided. Unnecessary surface treatment requirements should be avoided, otherwise, further processing may be required. 6. Design part tolerances to suit manufacturing techniques. Tolerances tighter than the process capability should be avoided, otherwise further processing or sorting will be required. Use bilateral tolerances, and avoid unilateral tolerances. 7. Design the product for foolproof installation. The configuration should be unambiguous. The components should be designed so that they can be assembled in only one way. Special geometrical features sometimes need to be added to components to prevent misassembly. 8. Minimize assembly directions. Oblique and conical shapes should be used in related parts. Design the assembly using the base parts to which other components are added. The assembly should be designed so that the components are added from one direction, usually vertically. Threads, screws, bolts, nuts, should be avoided where possible, especially when using automatic assembly. Instead, quick installation techniques such as various quick-release fasteners and gluing should be used. The number of separate fasteners should be minimized. 9. Minimize the use of flexible components. Flexible components include rubber parts, straps, gaskets, cables, etc. Flexible components are generally more difficult to handle and assemble. 10. Shape parts and products to facilitate packaging. The product must be designed in such a way that standard packaging compatible with automatic packaging equipment can be used. Shipping to the customer is easier. 11. Eliminate or reduce the need for adjustment. Adjustments are time-consuming. The need to adjust the product increases the potential for error. Next, let's take a similar picture of the design for additive manufacturing DFAM method, and go through it. Let's then take a quick look at how much these have in common. 1. Topology Optimization. Topology optimization is the optimization of a part geometry made using optimization feature of FEM software. Compared to other typical structure optimization techniques, such as size optimization or shape optimization, topology optimization can update the shape and topology of a part. Because topology optimization can help designers obtain optimal complex geometry for additive fabrication, this technique can be considered as one of the DFAM methods. 2. Multi-level structural design and lattice structures. Thanks to the properties of AM processes, geometrically complex parts can be implemented. This gives designers a great deal of design freedom to use cellular structures or lattice structures as both a very small structure and a normal-sized structure to achieve advantageous properties. Lattice structures implemented in different size classes can be used effectively to reduce weight. 3. Multi-material structure. In some of the methods of additive manufacturing, several materials can be used in printing, in which case the special desired properties are obtained locally in the part. In metal printing, this is possible, for example, via dead methods. 4. Mass customization. Because the manufacturer of additives can manufacture parts directly from the digital model of products, it significantly reduces the cost of manufacturing and delivery time for customized products. At its simplest, this can mean the serial number of the part, and at its most advanced, the fact that all the dimensions of the product are in line with the wishes of the individual customer. 5. Part consolidation. Due to the limitations of traditional manufacturing methods, some complex components are generally divided into several parts to facilitate manufacture and assembly. In redesign, parts of the original model can be combined into one complex part, and manufactured by additive manufacturing processes. This redesign process can be called component consolidation. It has been found that combining parts not only reduces the number of parts, but can also, in some cases, improve the functional performance of the product. 6. Post-processing minimization. Minimizing the post-processing of additional manufacturing parts primarily means designing so that the part requires as few support structures as possible, but the design can also affect the amount of other post-processing. For example, the threads are such a thing. 7. Functional and manufacturing properties in the same geometry. When geometric complexity does not significantly increase the cost of a part made by AM, many functional features can be combined into one part. Often, however, some of these require precise shapes, which typically need to be made by machining or other post-processing methods. Manufacturing properties are the shapes needed for automated part processing and various post-processing steps. For example, surfaces on which a part can be fixed by the machine screw clamp. The key principles of the design for manufacturing and assembly DFMA and the design for additive manufacturing DFAM methods are described here. Similarities are marked in the figure. In the laser powder bed fusion process, a powder layer is first applied on a building platform with a recoater. Then laser beam selectively melts the layer of powder. Then the platform is lowered by 0.0 to up to 0.100 mm and a new powder layer is applied. The laser beam melting operation is repeated. The process takes place in an inert shielding gas atmosphere. When recoating, melting cycle is repeated a few thousand cycles. The built part can be removed from the powder bed. The laser PBF process requires that the part be securely attached to the platform. Attachment to the platform can be done either directly, built directly on the platform, or using support structures. Support structures for LPBF processes serve several functions, including heat transfer, attachment of the part to the platform, compensating for residual stress-induced warping, and in support of a piece under construction. Left side. Faces with down skin angle less than limit normally require support structures. Right side. Faces with down skin angle more than limit do not require support structures. However, surface quality may be impaired. Left side. Holes diameter bigger than 8 mm needs support structure. There is often no need for support below diameter of 8 mm. Minimum recommended hole diameter is 0.4 mm. Right side. Hole geometry needs no support structures. Such shapes include droplet, triangle, inverted square, and other similar shapes. This picture is from standard. Most laser PBF systems use a blade or roller type recoating device. Depending on the thickness of the layer, with this type of application, the patterning can sometimes be disturbed, which is reflected as an error in the patterning of the next layer. The parts must therefore be oriented and arranged in such a way as to minimize the frictional forces generated during scraping. The following points should be taken into account. Longitudinal geometries should be oriented in a way that the contact length of the spreading system is minimized. Critical geometries should be oriented in a way that avoids parts being bent up if there is a contact between spreading system and part. A suitable angle is often 10 degrees. Multiple parts should be positioned in a way that the contact length of the spreading system is minimized. The design of the part and the printing position can affect the number of support structures, and thus the need for finishing. By positioning the part correctly on the platform, Unwanted curvature of the part can also be avoided. Long and thin pieces should be placed on their sides diagonally in the recoating direction. However, if it have to be placed on lap position, then in such angle that there is no large mass in one layer. The minimum wall thickness of a part depends on the material, the geometry of the part, and the printing parameters. The recommended minimum wall thickness is usually 0.2 mm. However, this is true for relatively small wall areas. If the wall sections are too thin or unsupported, the surface may buckle. The maximum length to height ratio is 8:1. Of course, if the part has a reasonable section or supporting geometry, then it is possible to build at a higher slender structure. Minimum strut diameter is usually 0.50 mm. As built part surface roughness RZ varies from 30 to 140 micrometers. Depending on the angle between the part surface and the build platform, the surface roughness noticeably differs. Vertical surfaces have the best surface quality, and the worst surface quality is on downward surfaces. Case FNTDMA Part Number 2 has been designed to collect features that are possible to implement with the lasered PBF method but that are almost impossible to implement with traditional manufacturing methods. This means that the product aims to have at least the following characteristics. The product consists of a circuit board and a 3D printable body. A complex internal structure consisting of cooling ducts and a nozzle structure. Post-processing minimization. In other words, some should not need support structures. Combination of functions. That is, the part that forms itself as a body and its different features of different functions. Lightness and durability. The part must be relatively light but must withstand handling and occasional drops to the floor. Visuality. The part must look interesting. Let's go through the story of the part from the designer's perspective. In the first stage, the product was viewed from an assembly point of view. The functional parts of the product are its legs, frame structure, self-cooling and cool surface structure, and electronics cooling internal structure. The cooling duct of the product must be efficient enough to transfer the heat generated by the electronics to the environment. 5 functional parts were found. 1. Feet. 2. Frame structure. 3. Shell structure. 4. Heat exchanger from electronics to coolant. 5. Heat exchanger from coolant to air. In the second stage, the structure was considered from a part point of view, taking into account the functional properties, mechanical properties and manufacturing requirements. Of course, the requirement that the part must look interesting was also considered here. The functional features have been reviewed in the first phase. The mechanical properties take into account lightness and durability. The manufacturing features take into account the fact that no support structures are used, and the structure of the part must be a good reflection of the possibilities of the manufacturing technique. After a few hours of thinking, and several cups of coffee, the idea began to take shape. 5 feet that are lightened so that they are hollow. Perforated outer casing. Frame structure with a cooling duct system including a nozzle structure. After that, a few hours of using 3D CAD software, and the results started to show. The material is aluminium Al-C10 Mg. The height of the part is 90 mm and the weight is 265 grams. The part consists of 5 hollow legs. The outermost has a perforated protective shell. The holes are made so that they are vertical. Inside the protective shell there is a frame structure consisting of a funnel-shaped outer part, and an inner structure contained in a helical cooling duct system. The cooling channels are teardrop-shaped. And here is the finished structure with the electronics. Another example is the design of the rocker arm of a bending fatigue machine. This example utilizes topology optimization and generative design software. The design of the bending fatigue machine has redesigned the approximately 50-year-old Carl Schenck bending fatigue machine so that the new machine can simultaneously fatigue 10 bending fatigue specimens at the same time. the design has utilized traditional design, FEM calculation, topology optimization and generative design optimization. The material chosen is aluminium Al-C10Mg. The starting point is a rocker lever weighing 350 grams, which in the first stage has been made lighter versions by simplifying geometry manually using FEM calculations. The weight is then reduced to 216 grams. The fatigue test results of the research group have been utilized in the design. When it is known that one fatigue test can last about 10 million cycles, and the device can do about 80 runs a year, it can be calculated that in 10 years the rocker arm will have about 8,000 million cycles. In the figure below, the Euler curve has been extended so that the resistance of the test material to ultra-long cycle fatigue can be estimated. The calculated tension of the rocker arm is not allowed to go above 20 megapascal. The maximum tension in the part in the picture is 8.15 megapascal. Here is a topology-optimized part with SolidWorks software. The part is printed as is, that is, no changes have been made to it after topology optimization. The weight is 215 grams. Here is a part designed with Autodesk Generative Design software. The weight is 136 grams. Generative Design software works by defining joint geometries, loads and areas where the material must not be in the part, and based on this the software calculates several alternative structures that implement boundary conditions. The picture shows all the pieces of the support structures. The design of Part D has best taken into account the support structures, and their removal. There are a lot of support structures in the generative design section. And finally, short conclusion. Part consolidation. Parts can be combined into one complex part, and manufactured by additive manufacturing processes. It has been found that combining parts not only reduces the number of parts, but can also, in some cases, improve the functional performance of the product. Post-processing minimization. Minimizing the post-processing of additional manufacturing parts primarily means designing so that the part requires as few support structures as possible, but the design can also affect the amount of other post-processing. For example, the threads, functional and manufacturing properties in the same geometry. When geometric complexity does not significantly increase the cost of a part made by AM, many functional features can be combined into one part. Manufacturing properties are the shapes needed for automated part processing and/or various post-processing steps. For example, surfaces on which a part can be fixed by the machine screw clamp. And here was our presentation. Thanks for your attention.